I mentioned a minute ago that the binomial tree approximates the log normal distribution because binomial returns are an approximation to normal returns, and when I exponentiate normal returns, I get the log normal distribution by definition. And it arises in the limit as h goes to 0. So when I say that if I look at stock prices, let's say I have stock prices at time t, and I look at stock prices at time S capital T, and I take that period and I break it up into n steps. So h is equal to t minus t over n. I break the time period up into n steps, and then I build a binomial lattice in those n steps using the earlier formulas. What we're saying is that if I used normal returns instead of the binomial returns, S capital T would automatically have a log normal distribution. If I use binomial returns, ST will have a binomial distribution. However, as h goes to 0, which means n goes to infinity, as the number of time steps gets bigger and bigger, my time intervals get smaller and smaller, the binomial distribution of stock prices will get closer and closer to the original log normal distribution. So here's our binomial model with the up and down movements, the associated probabilities calibrated in or notated in risk-neutral P. And so P star is the risk-neutral probability of an up. And this is the binomial lattice of stock prices. This is the distribution that becomes log normal. If I fix, this is the time point t, and this is the time point 0, and I take that interval of time and break it up into more and more steps, the distribution of prices I get at time capital T will become log normal. This is another way of looking at that same idea. So in this n-step binomial lattice, where it takes me n steps to get to my terminal stock prices, we've seen this expression before. All the stock prices at my nth step have the same form. The initial stock price, and then I have some number of u's and d's, but the total number is always n, because in each step of my lattice I either get a u or a d, and after n steps I have to get a total of n u's and d's. So there are n plus 1 prices here, because j can be 0, 1, all the way up to n. So if I take n steps in my binomial lattice, I have n plus 1 prices at expiry. And again, we've seen this formula before in the general price formula for a European option that I gave in an earlier module. On the risk-neutral probability of this stock is equal to the combinatorial coefficient times the probability. So these are binomial probabilities, where P star is the probability of an up. And it's easy to remember. U to the j requires a P star to the j. D to the n minus j requires a 1 minus P star to the n minus j. And then we have this standard combinatorial coefficient. Here's a figure from the book, and there's another figure in the book where the binomial tree is more crude. This is a binomial tree where there are 25 periods, so that's a pretty good value for n. And this is a picture where the boxes are the prices that come from the binomial tree and the associated probabilities, and the continuous curve is the theoretical log normal distribution that those prices converge to when n goes to infinity. So you can see even at n equal 25, I get a pretty good distribution of prices with the binomial. Certainly, if you looked very, very carefully in the tails of the distribution, you would notice more crudeness. But if you look in the book in an earlier figure, the author also provides where it's, I believe, a 5-step lattice, and you'll notice significantly more crudeness between the distribution of the 6 prices in the binomial and the log normal.